Trigonometry integrals are those which have just trig functions in them. And for example, here is the integral of cosine to the 6x times sine x dx. So there are several different types to think about in these trigonometric integrals, and this happens to be one of the easier ones. A simple the correct u substitution here will work very well. And so the key is that the derivative of cosine is minus sine x, and so I'm going to let my substitution variable be cosine. We'll let u equal to cosine x, then du would be minus sine x dx. So if I incorporate the negative sign here, so I'll put a negative inside here and a negative on the outside to compensate, then I've got this minus, and here is u to the 6th power, and sine x, negative sine x dx is du. So you see it turns into a simple polynomial term. And integrate this, we get minus u to the 7th over 7, and then resubstitute back in, and we end up with negative cosine to the 7th x over 7 plus a constant. So it turns out some of the friendliest trigonometric integrals are those in which we have both cosine and sine, and one of these is an odd power, and in this case sine to the 1st power, odd number. Alright, so let me give you a little tougher example here coming up. This one's a little bigger. The integral of cosine to the 5th x sine to the 4th x dx. And now these are friendly to work when at least one of those two functions has an odd power. When they're both even, we got some trouble. But whenever one has an odd power, then we want to let the other one be our substitution variable. You'll find out why here in a minute. And now if they were both odd powers, it wouldn't matter which one we substituted for, but the technique would be pretty similar either way. Alright, that probably doesn't make a lot of sense quite yet. So, but here's the secret to this. I'm going to rewrite this as the integral of sine to the 4th x, cosine to the 4th x, and then cosine x dx. Because I said I want to let u be sine x, because the differential of sine is cosine x dx. So this will end up being my du part. But I have a mix of two trig functions here. Well, the secret is to replace cosine to the 4th. And if you recall the Pythagorean identity, sine squared x plus cosine squared x equals to 1. If you solve for cosine squared, you get 1 minus sine squared. So we're going to use this identity quite a bit, or the other one, which would be cosine squared is 1 minus cosine squared. So file that away, and we're going to use that a few times here and throughout these videos. Alright, so I'm going to replace cosine to the 4th with cosine squared to the 2nd power. In other words, I end up with integral sine to the 4th x, parentheses, 1 minus sine squared x squared cosine x dx. And there we go. We need to multiply all that stuff out. I think just a little bit of experience speaking here, I'm going to go ahead and do my u substitution before I do this algebra. I don't want to have to do as much writing that way. So just a little nice tip. So I'm going to write my substitution up here. I'm going to let u be sine x, and then du would be cosine x dx. Alright, so here's du. And that becomes the integral of u to the 4th, parentheses 1 minus u squared squared du. Much nicer, isn't it? Much nicer function to work with. Alright, now we have to do the algebra, of course. So I'm going to erase this part, make room for it. And let's see what we have. This would be the integral u to the fourth. When I square this out, we have to FOIL it out. 1 minus u squared times 1 minus u squared. That gives us 1 minus 2 u squared plus u to the fourth, and then du. And then we have, well, do some more erasing. We have, I'll multiply through u to the fourth minus 2 u to the sixth plus u to the eighth, parentheses du. And now that presumably is an easy one. U to the fifth over 5 minus 2u to the seventh over 7 plus u to the ninth over 9. And let's write out the final answer. I'll replace the u's with signs. So I have sine to the fifth x over 5 minus 2 sine to the seventh x over 7 plus sine to the ninth x over 9 plus a constant. And there you have it. There you have it. So that's how you do that kind. Okay. Now whether both even, or if you just have a sine or a cosine to an even power, then that's going to demand that we use a different technique. So I'll do one of those next. I'll lead off with this this portion with a fairly easy one, the integral of cosine squared x times sine squared x dx. Now there is a different technique I'm going to show you after I work this one, but my main goal in this part, this example, is to show you how do you handle an even powers of cosines and sines. Alright, well, I'm going to first of all decide which trigonometry function to use. Do I want to use cosine, or do I want to use sine? And when it comes to integration, when you integrate cosine, you get a positive sine. So, whereas when you integrate sine, you get a negative cosine. So I think I'm going to stick with cosines here. That means I'm going to write cosine squared x, parentheses 1 minus cosine squared x, dx. Then we'll multiply that out. I'm integrating cosine squared x minus cosine to the fourth x, dx. Alright, well, as you can see from the previous example, now it's inconvenient because I don't have an easy substitution to make. If I let u be cosine, then du is going to be negative sine, and there's no sine x in here. Alright, but here's how we get around this. We need to call upon the half angle formula, in this case for cosine. Cosine squared x is 1 plus cosine 2x over 2. So I would file that one away, and it's a very handy formula. And while I'm at it, let me go ahead and give you the sign. These you can always look up. Sine squared is 1 minus cosine 2x over 2. Now I don't need this one for this example, but those are the two they're called half angle formulas, I guess because x is a half angle of 2x. It's probably where it gets its name. Well, so I'm going to replace cosine squared with this. I'll replace cosine to the fourth with this thing squared. It's going to get a little messy. I end up with 1 plus cosine 2x over 2 minus parentheses 1 plus cosine 2x over 2 squared, and then dx. So there we go. And it's going to be a mess. Now I'd rather not mess with the fractions. My common denominator will be 4, won't it? Because this will be 2 squared is 4. There's 2. So if I multiply this by 2 over 2, I get a 4 here. So let's factor out the 1/4. And I've got 2, so I had to put 2 over 2 here. 2 times this top, 1 plus cosine 2x. And then minus, parentheses 1 plus 2 cosine squared 2x. No, that's not right, is it? Okay. 1 plus 2 cosine 2x, and then plus cosine squared 2x, all dx. Okay, so I usually try to enclose the whole integrand in parentheses or brackets, but there we go. All right, well, as you can tell, this one's starting to get pretty long-winded, and if you have higher powers than this, good luck. Okay, maybe I'll do one in these videos just to show you that it can be done. They do get kind of messy. All right, so I actually can integrate everything here except for that term. I'm going to have to apply the half-angle formula again to this part, and we'll end up with a cosine 4x in it. All right, so I'm going to erase all this part, and I'm going to multiply that out. When I multiply the 2 through here and remove the minus sign, I get this big long expression, and something rather nice happens here. The 2 cosine 2x and the minus 2 cosine x cancel one another, and I've got 2 minus 1, that'll be 1. So I end up with 1/4 integral of 1 minus cosine squared 2x. All right, rather remarkable. So that simplified very nicely for us, and but I still now this would be 1 minus sine squared 2x. That wouldn't help us either. Either way, we could turn that to sine if we wanted to. In fact, I think I will. Because 1 minus cosine squared is sine squared, and because I have kind of a reason for doing this that I'll reveal afterwards. Okay, this is sine squared 2x dx. All right, so let me erase all this mess down here, and then I'm going to use the half-angle formula on sine squared, so it's 1/4, and the half-angle formula is 1 minus cosine 4x over 2 dx. So this time I've got to double the 2x to make it 4x, and we end up with 1/8 integral 1 minus cosine 4x parentheses dx. We'll integrate this. I get x, and we'll work with that, 1/8. So I end up with x minus, integrate cosine, you get sine. It'll be sine of 4x over 4. And because if you went backwards and took this derivative, you would get cosine 4x times 4, because the chain rule, we need that 4 to cancel. So that's where that extra 4 comes into play. I can write my plus c, I suppose, and be done. I think a lot of books would, or maybe a lot of instructors would go ahead and combine these and get factor out the fourth. So that's 1 over 32 parentheses 4x minus sine 4x plus constant. All right, so there we go. That's applying the half-angle formulas to solve a combination of sines and cosines where the powers are all even. So, all right, now I'm going to erase from down below here. I'm going to show you another way to do this one, and I don't think you'll get to use this technique a lot, but I think it's worth a look. So I'll erase this, and I want to do this a separate way. I kept the problem and its answer up there. And what I want to point out is that when you see cosine times sine, that's half of the sine of 2x. Okay, so there's another identity in trig, which I'm sure you've seen somewhere, that 2 cosine x sine x is equal to the sine of 2x. Now that one's called the double angle identity for sine. And it's sure is a nice one to know. So I have the cosine x sine x, but it's squared. It's squared. So if you think about this, first of all, let's divide it by 2. If I square this, I'll get sine squared 2x over 4. So this gives me 1/4 sine squared 2x dx. So again, this is the square of that expression. So I have sine squared 2x over 4. I pulled the 1/4 out. All right. Now then, here we go. Half angle formula, because we have an even power sine. So this would be 1/4 integral 1 minus the cosine of 4x over 2. All right. And so the half angle formula doubles this angle, okay? And there we go. So you can now we can integrate this because that's cosine to the first power. So I'm going to bring the 2 out, so it'll be 1/8. And inside I have x minus sine 4x over 4. And I think it's looking like that up there. In fact, if I get my common denominator, factor out the 4, 1 over 32, 4x minus sine 4x plus a constant, and equal to what we originally got, as it's supposed to. So there you go. I wanted to show you the double angle identity, because once in a while that comes in pretty handy as well. In fact, I thought this problem was shorter by using it. Okay, let's go on to another problem. Next we'll dive into the secant tangent format. And so, previous video we did sine and cosine format. Here is secant tangent format. What about cosecant and cotangent? Well, if they're together, you could invert and get secant tangent. Problem solved. We're back to this kind of format here. If you have a mix, for example, suppose you had a cosine to a power times a tangent to a power. Well, if you write tangent as sine over cosine, then this cosine power is going to do some cancellation with the tangent function, and you'll be back to sine and cosines together. And so it turns out any configuration of positive integer powers, I guess negative integer powers, because you could have denominators also, any configuration of those will eventually, you can get to either the sine cosine format or the secant tangent format. And in all those formats, one of those functions could be missing. In other words, you could have a sine to the 5th power or a tangent to the 4th power. Alright. Well, what do you do with a secant tangent format? And the secret here is the secant is to the 4th power, so we're in good shape. That's what we want. And the idea is that the derivative of tangent is secant squared. And so the differential of the tangent function is going to be secant squared times dx. So as long as I can hang on to a secant squared dx will give me the differential of the tangent. In other words, I want to let my substitution variable be tangent. So if you didn't quite follow that, don't worry about it. I'm going to show all the work here. So here is the idea. We want to write this as secant squared x tangent cubed x dx. And there's an identity for secant squared. Now let's get that identity. If you too lazy to look it up, or you get stranded on a desert island and you don't remember how it goes, at least remember cosine squared x plus sine squared x equals to 1. And if I divide everything by cosine squared x, we'll get 1 plus sine over cosine is tangent, so that's tangent squared. Tangent squared x equals 2. 1 over cosine squared is secant squared. Alright, so I can replace secant squared with 1 plus tangent squared. So it's in case you can't remember the exact order here, and you can't look it up, you can always work it out pretty quick. I do that all the time because I don't always remember that so well. All right, so I'm going to replace this with 1 plus tangent squared. I have this secant squared. In fact, I'm going to put this secant squared over here. So this part will be 1 plus tangent squared x times tangent cubed x. and then I have secant squared x dx. So I think we have accounted for all the pieces. All right. So now we got them where we want them. My substitution variable is going to be tangent. So if I let u be the tangent of x, du will be secant squared x dx. So there's my du, and here I've got 1 plus u squared times u cubed. So plug all that stuff in. 1 plus u squared times u to the third power du. And shaping up very friendly here. Multiply this out. Integrate u to the third plus u to the fifth du. And integrate, we have u to the fourth over 4 plus u to the sixth over 6. And let's put our x's back in. This will be tangent to the fourth x over 4 plus tangent to the sixth x over 6 plus our constant. So and there we go. This, I suppose this could be dressed up a little bit, but I think I'll leave the answer that way right there. So that was the secret here. If you have a even power secant in your problem, then make sure you keep out a secant squared. If you have a higher power, then you've got to turn it into tangents. Turn all the rest of it into tangents, and let tangent be your substitution variable, and things will work very smoothly like this. So that's this one's not so bad, is it? All right, let's go on to a different case of the secant tangent functions. Here we have the integral of secant cubed tangent cubed dx, and what makes this one pretty doable is the fact that I have an odd power of tangent. Now, in the previous example, when the secant power was even, then we knew how to substitute for those. But when the secant is odd, if the tangent is odd, then we're in pretty good shape. And the idea is that we want to keep out a secant tangent. I'll show you why here. So I'm going to factor out the secant squared x, tangent squared x, and then secant x, tangent x, dx. Now, the derivative of secant is secant times tangent. So this is you might say this is the differential of the secant function. It would be secant x, tangent x, dx. Yeah, I forgot to put my tangent x in, didn't I? So I'm always kind of a stickler about those details, so I better get it right myself. Alright, so when tangent is an odd power, then keep a secant tangent out, and then work from there. Now I want to actually use secant for my substitution variable here, because the derivative of secant is secant times tangent. So I want all this in terms of secant, and so this is secant squared x. Tangent squared x, I can never remember all these reliably. Tangent squared is secant squared x minus 1. All right. One of these days maybe I'll get that memorized. And then I've got secant x, tangent x dx. Well, like I said, our substitution variable is going to be u equal to secant x. So I let u be secant x, du is going to be secant x, tangent x dx. So there's my du part, and these are u's. So we have integral u squared, parentheses u squared minus 1, times du, and now it's pretty friendly, isn't it? I'll finish it here. This is going to be u to the fourth minus u squared du. So we have u to the fifth over 5 minus u to the third over 3. And we'll have a plus constant here, but don't forget to put it back in terms of x. So I'll write the answer up top here. It will be secant to the fifth x over 5 minus secant cubed x over 3 plus a constant. So there's that case. When tangent is odd, it really doesn't matter so much what secant is, because we're going to substitute for secant. So secant can be even or odd, doesn't matter. But when tangent's odd, then you have a nice substitution, and using secant function works out very nicely. All right, so the first case was when the secant function was even. The second case was when the tangent function was odd. So what if, so secant even and tangent odd. So what happens if secant is odd and tangent is even? Let's look at one of those. Okay, so I'll erase the board and I'll put one up here. Here is one of those exceptional cases where the secant has an odd power and the tangent has an even power. Now, generally speaking, there is no set way for solving those, and they all carry their own little tricks. And I can't say I've done many of them at all. I can't remember the last time I did one other than integrating secant cubed, which I had to do because I put secant cubed on a test by accident a couple years ago, and one of my students actually solved it during the test, which was pretty remarkable because it's tricky. It's very tricky. And so, but we'll see what happens here. Integrating secant x, tangent squared x, and I believe the trick here is I'm going to replace tangent squared with secant squared minus 1. So that becomes the integral of secant x, parentheses, secant squared x minus 1 dx. Okay, and is that good? I don't know. We end up with secant cubed x minus secant x dx. And I think we're going to be okay, because I know I've done this one before. And secant, we can integrate secant. It's the natural log of secant x plus tangent x, I believe. I'm going to look that up to make sure, because I don't have all this memorized as well as I would like to. But this one right here, that one right there, I'm going to use an integration by parts strategy here. Now, I don't think it's obvious at all that you should use integration by parts or how to do it. But here's the trick, because I have done this before. That's supposed to read secant cubed. Let me write that a little more clearly. Secant cubed x dx. Okay, I'm going to let u be secant x, and dv is secant squared x dx. Okay, now I don't think that's very obvious, but the advantage is that the v will be tangent, because the integral of secant squared is tangent, or the derivative of tangent is secant squared. And here I got to remember that the derivative of secant is secant times tangent, secant x tangent x dx. Alright, so I kind of ran those together, sorry about that. So when I plug these in, I have u times v, secant tangent, secant x tangent x, minus the integral of v times du. So I multiply these together, I'm going to get secant times tangent squared dx. Secant x tangent squared x dx. And isn't that funny? Because there it is. There it is. Am I going in circles? We'll find out. I think we're going to be okay, because I'm going to solve for this using everything else. So, all right, so hopefully you follow this part to here. Now I'm going to replace it here, because I have to subtract secant. All right, so hopefully I can remember this stuff. That's, I'll erase it, I'll get it up on the board for you. Well, I got it all put together. The secant cubed, the work we did a minute ago on secant cubed, ended up being secant x tangent x minus integral secant x tangent squared x dx, and then the minus secant x goes here. So let's do something kind of nice here. This is my original problem. I'm going to call that I for integral. And look what, here is I here. Now I've got I on both sides. The nice thing is that this is a minus I. So if I add this integral over here, I have 2 times I. 2 times my original problem will equal to what's left over, which is secant x tangent x minus the integral of secant x dx. So kind of a nice turn of events here. I got to tell you, when you have this form with the power of secant odd and the power of tangent even, I'm thinking you don't often encounter this trick. Okay, but I'm not an authority on this because I have not done a lot of these. Okay, I got to tell you. But I'm kind of pleased how this one's turning out. It's not bad. But I think in real practice, I would just go look for some kind of reduction formula or integral table formula when you have this format, and not worry about this too much. That's if you're in a class with an instructor who's okay with that. Okay, so all right, we integrate secant, and I believe it's the let me make sure I got it right here. It's a natural log of something. So like I say, I don't have all these memorized. Natural log, absolute value, secant x plus tangent x. So my original problem will be 1/2 of what I get over here. 1/2 secant x tangent x, and then minus the natural log absolute value secant x plus tangent x. Alright. Plus a constant. Now, why the integral of secant is this natural log secant plus tangent? That can be worked out somewhere else. And we generally, I think I usually work that out when I teach the derivative of trig functions, but hopefully you've seen it somewhere. But this time I just looked it up. Okay, so there's the answer. It was doable, and this is not as bad as probably the higher power versions of this. So now we have basically introduced the essentials of trigonometric integrals, and you have the 2 cases, separate cases for sines and cosines, and you hope that at least one of them has an odd power. Otherwise you have to use the half angle formula, which is a little more work. Or if you have secant and tangent, there are 2 cases there. One where secant has an even power, or one where tangent has an odd power. If you have this exception here, then good luck. Okay, there is no set standard way to solve it. So, but anyway, that is the introduction. Those are the basics of the trigonometric integrals. So, all right. Next, we'll go on to trigonometric substitution.